Dr. Rico here. This is an introduction to my mini course, Robotic Planning and Kinematics. The syllabus link and notes are in the description. Okay, 1.5, the completeness of the bug 1 algorithm. Okay, so going back to the bug 1 algorithm, not the bug 2 algorithm. Here, we follow up on our previous discussions and formally define the completeness of an algorithm. Definition 2.3, an algorithm is complete if, in finite time, 1, it finds a solution, i.e. a path, if a solution in fact exists, or 2, it terminates with a failure decision if no solution exists. Next, we establish that one of our proposed algorithms is indeed complete. This result was originally obtained by Lumaleski and Stepanov, so check out that paper. Theorem 2.4, the completeness for bug 1. The bug 1 algorithm is complete under the modeling assumption stated early in the chapter. So that's the theorem. We will prove it soon. On the geometry of closed curves. To prove Theorem 1.4, we start by introducing a wonderful and useful geometric result. Theorem 2.5, the Jordan curve theorem. Every non-self-intersecting continuous closed curve divides the plane into 2 connected parts, okay? One part is bounded, called the inside, and the other part is unbounded, called the outside. And the curve is the boundary of both parts, okay? So this figure shows it. You have an inside and you have an outside. As long as the continuous closed curve is not self-intersecting, we have these 2 regions of the space that are defined, okay? Next, consider the following. Imagine that the curve describes the boundary of the obstacle. Given a start and goal point outside the curve, obstacle, connect the 2 points using a straight segment and count the number of intersections between the segment and the boundary of the obstacle. It is easy to see that this number of intersections must be even, where we regard 0 as an even number. Each time the segment enters inside of the curve, it must then return to the outside, okay? A few examples are given here. So we see 0 intersections, 1 intersection, 2 intersections, okay? So this one entered, it had to leave, so therefore it has 2. Here we go. Every time it enters, it has to leave. This is a sort of what goes up must come down situation. So that's what we've got. Some more examples there. The proof of the completeness theorem. Here we prove Theorem 1.4. Recall that the bug 1 algorithm is presented in pseudocode and a flowchart in section 1.3, okay, where we had a few different possible outcomes of it, and so we'll kind of walk through that in this. By contradiction, assume bug 1 does not find a path, even if a path exists. So remember, the completeness theorem says that if a path exists, the algorithm will find it, right? So we're going to prove that the opposite is false, which means that it must be true. All right, so the opposite then is to assume that the bug does not find a path, even if a path exists. So let us prove the theorem by contradiction. That is, we assume the bug 1 is incomplete and find a contradiction to that. Consider the situation when a path from start to goal does exist, but bug 1 does not find it. The flowchart description of bug 1 implies the following statement. Okay, this was the bug 1 algorithm flowchart. If bug 1 does not find the path, then necessarily bug 1 will either terminate in failure in finite time or keep cycling forever. Those are the only other possible outcomes in the bug 1 algorithm. So there were 3 to start, which was that it finds a path if it exists, which we said it isn't finding the path, so we're getting rid of that possibility. Okay, so the other 2 possible are that it can terminate in failure in finite time, or it can keep cycling forever. Now we just need to prove that neither of these things can happen. So bug 1 cannot keep cycling forever. Okay, so suppose bug 1 cycles forever. Because there is a finite number of obstacles, the presence of an infinite cycle implies the robot must hit the same obstacle more than once. Now, during the execution of bug 1, the distance to the goal is a function of time that is monotonically decreasing when the robot is away from any obstacle, right? Moreover, when the robot hits an obstacle, the distance from P leave to the goal is strictly lower than the distance from P hit to the goal. This fact can be seen geometrically. This is a requirement in the algorithm. Therefore, when the robot leaves an obstacle, it is closer to the goal than any point on the obstacle, any other point on the obstacle. Hence, bug 1 cannot hit the same obstacle twice, just like you can't step in the same river twice, right? Okay, so that was the cycling. So we restricted ourselves down. We made the assumption that our theorem was incorrect, and then we said, okay, so that gets rid of the first of the three possibilities of the algorithm ending. So we can't find the path. That was the first one that we eliminated. The second one was that we cannot keep cycling forever. That is impossible by this argument here. So we have one more possibility, which is that the bug 1 ends in failure, but we're going to show that that's not true. That's not possible. So if bug 1 is incomplete and a path actually exists, then the only possible result is that it terminates in failure, as we've just deduced. According to the bug 1 flowchart, failure can occur when the robot visits all the obstacle boundary points reachable from the hit point, moves to the boundary point, P leave, closest to the goal, and is unable to move towards the goal. Consider now the segment from P leave to the goal point. Because a path exists from start to goal, a path must exist between P leave and the goal. By the Jordan curve theorem, there must be an even number of intersections between this segment and the obstacle boundary. Since P leave is one intersection, there must exist at least one other one. Let P other be the intersection point closest to the goal. Now, the point P other has the following properties. It lies on the obstacle boundary. It is reachable from P leave because it is reachable from the goal. And 3, it's closer to the goal than P leave. These facts are together a contradiction with the definition of P leave. Okay, so let's take a look at a situation like this. We start off here, we head toward the goal, we hit. So remember, we're looking at a case where there is a path that exists to the goal. So here's the path from start to goal that does exist, all right? And we're assuming that there's a situation where a path can exist and we don't find that path, okay? So we start here, we hit, okay? We go to here and say we leave and we head toward the goal. And if we were to say, okay, it's going to go into an obstacle now, so it must leave the obstacle. So there's the second and even number of points on that line. And if we tried to go to here, what we would see is that P other should be what P leave is. And so that can't happen, okay? So this is why it's a contradiction with the definition of P leave. P leave is by definition the point that's closest on the object to the goal. And here we have a point that's closer. So that's a contradiction. So by contradiction, we have proven that the bug 1 algorithm is complete. It always finds a solution if a solution exists. All right. That's all we've got for this chapter. There's also an appendix on operations on sets, and I do recommend you check that out as well, even though it's just a lowly appendix. All right. See you next time.